Hello everyone. In this video, we are going to talk about something that you probably have seen when you entered a highway or exited the highway through a ramp. You might have seen that the ramp has this side angle, which we call banking, or you might call it super elevation, this sideways slope. And you might wonder why there is this angle, this side angle. Well, the reason is when you go on an arc, any arc with the radius r, and the velocity, if you keep the magnitude of velocity v, the force that you need to do this kind of rotary motion, the force that is toward the center, Fc, or centripetal force, is equal to m times v squared over r, which is the centripetal acceleration. Okay, so you need that force. Where does that force come from? If the road has no angle or anything, it has to come from the friction under the tires, the sideways friction. So if you look here, you're looking at the car that is coming at you and going around this circle, basically. So if you look at the free body diagram of the car, the radius is r here, right? And there are three forces on the object. There is a normal force from the ramp in general, there is mg, and there is friction. Now, the direction of this friction depends on how the car is going. So if the car is just stationary and not moving on the road, then the car wants to go down because this mg has two components, correct? It has this component mg cosine and it has this component mg sine, which wants to slide it down. So friction should be upward to stop it from sliding down. This is when the car is not moving, okay, or stationary or moving at very small speed. So this mg component is going to slide the part down. Now, when you're going super fast, okay, you need some big force toward the center, which we call centripetal force, and that force is the one that you need to go around the circle, right? Because you are constantly changing the direction of your speed, or velocity. So in that case, actually your car has the tendency to escape this way, but your friction is stopping it. So friction is basically toward the bottom of the slope instead of the outside. Another thing that some books do is, instead of showing it this way, they say, well, there is this imaginary force which we call centrifugal force, okay? And this force is basically like this, F of centrifugal, and that is mv squared over r. And now they say with these four forces, the object is at equilibrium, and they say some of the force along, let's say this direction is zero and this direction, or this direction zero and this direction. Okay, and they can find basically the condition for equilibrium. But here, since we don't deal with this imaginary force of centrifugal, here we look at the centripetal acceleration, v squared over r, and we use the nt coordinate. So t, tangential direction, here is out of the board because the car is moving toward us, n is toward the center, and binormal is upward. So if I write some of the forces in the normal and the binormal directions, in the normal direction, the component of F that you have is F cosine theta, right? So if you draw a horizontal line here, this angle also is theta. So F has a cosine theta in the n direction, and n, if you look at it, n has two components. This one here is n sine theta, and that will also help create this centripetal force. And then in the binormal direction, mg is downward, f sine theta is downward, as you can see, and n cosine theta is upward. So these are the two equations, and the car does not go up and down, it stays at the same elevation. So in the binormal direction, acceleration is zero. So these are the two equations that I have for the motion of the system. And now I can show you why is it that the road is banked. So let's take a look at that. The reason is this. Here, as I said, if the road is flat, if there is no angle, okay, so theta is 0, what's happening? This becomes 1, this becomes 0. You see, the only force that is creating the centripetal acceleration for you is the lateral friction of the tires with the road. Now, we cannot always rely on that lateral friction to give us this required v squared over r. Why not? Because many times the road could be wet, could be there is rain, there is ice, or anything else, and your friction, this maximum of this force, is going to be small, and there is a chance that when you go on the slope, you can easily slide sideways and get out of the ramp. So since the road friction is not always reliable, what do we do here? We are basically, adding a secondary component. Not only F is there, also N, this component of N, this guy here, this component is also helping me to create some extra force to keep my centripetal acceleration. So you see the component of N, the horizontal component of N, is helping the friction to create that acceleration. That is why. And you might say, well, guess what? When instead of F, I have F cosine theta. F cosine theta is less than F because cosine theta is less than 1. You're right. But the thing is this. This angle that they typically pick for these roads, these ramps, this is a very small angle. Typically, this theta is something like 8 to 11 degrees, something like that. Okay, so cosine of these angles is very small, okay? Cosine of 8 or 10 degrees or something, this is something like 0.9 or so, and sine of that is, although not big, but big enough that this component of N can help. Actually, for 8 degrees, this is 0.99, and this guy is 0.14. So look here. This is almost the same as it used to be, but now like 14% of this N, which is related to mg, is also going to come to help. So overall, this force, if you plot this thing, clearly this is going to be bigger than just the F that you had. For all different angles, you can see that when this angle is bigger than 0, this guy here is going to be bigger than friction alone. Okay? And especially when this friction is very small, this term still exists. This term still can provide the centripetal force. So, you might say, with that condition, what is the maximum speed that I can exit a ramp or enter a ramp, right? What is the maximum? Because we have seen on the road signs that it says, hey, on the highway, when you were going straight, the speed was like 75 miles. But when you get to the ramp, you see that the 75 miles all of a sudden go down to 40 miles. So why is it that your speed is reduced when you are exiting or entering the ramp? How much? How would you determine this number? Where does this number come from? So for that, we look at these two equations. And here I show you all different scenarios. Scenario 1 is there is no ramp. The road is flat. You only rely on a friction, static friction, for which the maximum is mu s times n. So that F, I'm going to replace it with mu s times n. And the slope is 0. Now, what is this E parameter here? This E is basically the tangent of that angle. So the tangent of the slope, E, which is the amount of rise over the width, this is the parameter that we call super elevation or banking, E, tangent of the angle. And here we assume that E is 0, or basically theta is 0 because E is tangent of theta. So, and for F max, we use mu s times n max. So we go back to these equations. Look what happens. When theta is 0, you get a 1, you get a 0, 0, and a 1. From the bottom one, you can clearly see that n is equal to mg. And this f, remember, I'm going to replace maximum of it by mu s times n. So this v also is going to be v max. And this n that you have here is going to be replaced by mg. So if you do that, you get mv squared max over r is going to be mu s times mg. The m's would cancel. You multiply both sides by r, take a square root, and this is the maximum speed that you can exit a ramp if there is no banking, mu sgr. Okay, so the formula for exit ramp, if there is no banking, the Vmax is square root mu sgr. Now, on the other hand, if there is no friction, which is not really common, it's not realistic that the road has no friction, but let's say it's completely icy road, but there is angle. So if there is no friction, can the angle alone give me a possible maximum speed? Yes. In this case, we set f to 0, but e is non-zero. So wherever there is f, we're gonna set it to 0. So from here, you can see that n is mg over cosine theta, and plug it right up here. So you get mg tangent of theta, or mg e, because tangent of theta is e, equals me mv squared over r. Again, m's cancel, multiply by r, take a square root, and you get Vmax equals the square root of eg over r. So this is if you have banking and no friction. Now, which one of these two is bigger? Typically, the top one is bigger because mu s is typically much bigger than e. Because e is tangent of a small angle, like for instance 14 degrees or so, huh? So if I go ahead and use tangent of 8 degrees, you see it's about 14.14. So this guy is something like 0.14, while the mu for a typical road can be quite a bit bigger than that, depending on the road. This guy can be 0.2, 0.3, 0.4 or something. So most of the time, this is bigger. Okay, now what if you have both, which is the most realistic case? So you have the banking and you have a maximum friction mu s times n. What you need to do in this case is you eliminate n between these two equations. So from the bottom one, you solve for n, right? N is going to be mg plus f sine theta over cosine theta. And this is going to go right there. And this f is going to be mu s times n, so that n is also going to replace here. And then you solve for v. And if you do that, this is your formula. Vmax is the square root Rg times E plus mu over 1 minus E times mu. And clearly, the advantage is now clear. This one is bigger than both of the previous cases. Why? Because if you look at this ratio here, the denominator of this denominator is less than 1 because E and mu are both positive. Since this is less than 1, that means this whole thing is clearly bigger than E plus mu. Since it's bigger than E and mu, which is bigger than E and bigger than mu, clearly this Vmax that you get is more than both of them. Of course, because both of them are helping. The banking is helping, the friction is helping. When you have both, you can have a bigger maximum exit velocity. Do you see that? So the advantage is clearly a bigger maximum exit or entry speed. And if friction drops, the other one can accommodate. Okay? Yes? So here is a table that you can see some numbers for comparison. And in this table, the F that you see actually is mu. It's not the friction force, so this F that you see here is actually mu. So look at scenarios here. Here we assume that the radius of the ramp is 50 meters. And we consider this 3 separate scenarios: flat road with friction, bank only, no friction, and then both. And these are the maximum speeds in miles per hour. Look at them. So if you go only flat ramp, 17 miles. If you go bank only, no friction, 12 miles. If you do both, you can go to 21 miles with a radius of 50. Now, if the radius is bigger, of course, since your turning is much more moderate, it's not as sharp, you can have bigger speeds. And you can see that. Flat road 29, bank only 21, both of them 36. And if the radius is even bigger, 300 meters, now look, flat is 42, banking is 29, and both is 51 here. You see that? So in this case, this one is definitely bigger than both of those cases. So this is one big advantage of banking on the roads. Now, is that the only one? No, there is another advantage. What is that? So here we want to consider the second scenario. So this time the car is not going as fast as possible, so it cannot slide this way because it's going very slow or almost like standing. The car has a tendency to slide down. As I just told you, this mg has this mg sine component, and this mg sine component wants to drag the car down. That centrifugal force, if you want to use it, is not big enough, so the car wants to slide down. In this case, the direction of friction is going to be opposite. It's going to be this direction. And so if you look at the equations of motion, everything is like previous case except the signs for F are exactly opposite this time. Look, last time you have positive F, negative F. This time you have negative F, positive F, because the F is reversed. Everything else is the same. And if you, again, solve n from the bottom one, plug it in the top one, and for this F, use mu s times n, then the V that you can find is V minimum. So this is the minimum that you can move on a ramp. So pay attention when you are going on a ramp. If the ramp has a slope, there is also a V minimum. If the ramp has no slope, then there is no V minimum because the car will never move this way. There is no mg sine component. So you don't need to basically have a minimum speed or anything. So this formula is only valid when there is some slope. Okay? Now look at this scenario here. Here, we evaluated this formula for a radius of 50. First, we assume that the road is flat. As I said, if it's flat, there is no V minimum. If the road has no friction and just banking, then minimum speed that you need to go on the ramp so you don't slide is 5.4 meters per second or 12 miles. If you go any slower than this, you're going to go down the slope because you have a 0.06, right? Which means your angle is probably like 3-4 degrees or so. Now, if you have both, look what happens. Again, you have no minimum speed. What does that mean? It means, yes, you have a slope. Your object wants to go down, but guess what? The friction doesn't let it. Look here. Look at your B or N direction. You can see clearly that this negative component and this positive would cancel each other. Okay? Yeah? Or these two are canceling this one. So clearly, because the friction is upward and the mg sine component is downward and they cancel each other, if you have some specific condition, your car will never slide down. What condition do you need? Well, clearly, for that condition, you can look at this formula. For this formula to exist, under the square root should be positive, and everything is good except for this numerator. So this guy has to be positive. That means E should be basically bigger than mu. So if E is bigger than or equal mu s, then there is a V minimum. But if you don't want any V minimum, in other words, friction is bigger than mg, then this guy should be negative. For that to be negative, E should be less than mu s. So if your tangent of theta is less than mu s, which we call it the locking condition on a slope, self-locking condition, clearly there will be no minimum. The object is already stable on the surface. So you see here, there is no minimum. There we go. So do you see the second advantage? The second advantage is, compared to bank only, is this time you don't need to go as slow, anything above 12 miles to not slow down. You can just go with any speed you like, 2 miles, 3 miles, even stay stationary. Don't move on the ramp. You're not going to slide down. Because what? Because in this case, this mu, as I said, F is the same as mu in this case, this mu is bigger than this E. This 0.012 is bigger than 0.06, so you don't have any minimum. And you can see the same thing for bigger radii, it's the same thing. Even for bigger radii here, you see that now 21 miles is the minimum that you need to go. But if you have both, there is no minimum. For 300, the minimum is 29 to go. But again, if it's what? If it's both, you don't have a minimum. Do you see that? So two advantages. One, it increases V maximum on the ramp. Two, it removes or eliminates the V minimum as long as this condition is valid. As long as you don't make your angle so much that the tangent of it is not bigger than the coefficient of static friction, you are safe. You can just park it on the slope and it's not going to go down. So this was the super elevation or banking on the ramps with their explanations and formulas. Hopefully you enjoyed the video. I'll see you in the next lecture.